Hey, y'all. Welcome back. In this video, we're going to be taking a look at how we can place numbers into scientific notation and take them out of scientific notation. And then in the next video, we're going to talk about how to actually perform operations on numbers that are in scientific notation. I want to start with a perhaps seemingly unrelated question. We are going to talk about stats towards the end of this course, but the general idea of statistics is you're going to take a sample from a large population and then try to use that sample to make guesses about the population from which that sample came. So let's say that our population is Wellesley students, which has about 2,500 students. How many ways do you think there are to choose a sample of size 10 from those 2,500 students? Hundreds, thousands, millions? Turns out it's quite a bit more than that. It's actually going to be 2.5 octillion different ways to choose 10 Wellesley students from the 2,500 students on campus. So you don't need to know any of this stat stuff. What I want to focus on is this big chunky number right here. Right? It's very large, takes up a lot of space on the page, right? And it's actually a little bit, besides being tedious to write, it's very easy to forget zeros. If you accidentally forget some zeros, your number is going to be accidentally smaller than you mean it to be. Okay? So what I want to talk about here is ways to write this more concisely, especially if you are going into physics or chemistry or biology or statistics or certain other disciplines. This is going to be fairly important because you're going to run into very large numbers quite frequently. So if we're thinking of ways to rewrite this, right, let's maybe take advantage of all of these zeros here somehow. There's 26 of them. So perhaps instead of writing the number like this, I could break up the 25 and the rest of the zeros somehow. Right? I could make this 25 times 100, this should be 100 septillion. That's not really better though, right? This is still taking up just as much space. But now we have a power of 10 on this right-hand side. Right? So maybe I could write it as 25 times 10 to the 26. Remember that if I take 10 to the c, where c is some positive integer, that's the same as 1 followed by c zeros after it. So since there are 26 zeros here, this can be written as 10 to the 26. So this is already quite a bit better, right? This is not taking up nearly as much space. There's only one more step before we can get it into scientific notation. This step is just a standardizing step, just to say that, okay, now this is officially in scientific notation to give us some guidelines for what that means, right? In order to be in scientific notation, the first number, which is called the coefficient here, has to be between 1 and 10, right? So we need to somehow make this 25 into perhaps a 2.5. Right? So to do that, notice that 25 times 10 to the 26 is the same as 2.5 times 10 times 10 to the 26, basically splitting this 25 into 2.5 times 10. Okay. If I wanted to, I could take this 10 and basically bump it over to the 10 to the 26. Remember that that multiplication doesn't really matter what order you do the operations in. I could go 10 times this, right, times 2.5, right? So let me maybe move the parentheses over. And now if you remember your multiplication rules for exponents, this is the same as 2.5 times 10 to the 27. Okay, so now I have pushed this into scientific notation. Right? I know this has been a little bit kind of feel through the dark to get to this point. We'll give an explicit algorithm for how to put something in scientific notation first. Right? But this is in scientific notation because it consists of two numbers. One, which is again called the coefficient, is a number that's between 1 and 10, and then that's multiplied by 10 raised to some power. This is a positive number. The rule is very similar for putting negative numbers in scientific notation. They have to be greater than -10 and at most -1 times a power of 10. Now, there is a jingle that goes along with this. I will sing it for you exactly once. Scientific notation, we will learn this hour. The first number between 1 and 10 times 10 to the proper power. So that's how I remember it. Let's do another example of a very large number. The sun has a mass of this number, right? This many, many, many kilograms. Let's try to put this in scientific notation. And I'm going to here give you an actual explicit algorithm, an explicit set of steps to go through. Step 1, find the first digit that is not a 0. Right here, it's going to be that 1. Step 2, place a decimal place after that first digit, and then write as many following digits until only zeros remain. So here, 1.989. At the end of step 2, you have your coefficient, the thing that you're going to multiply by the power of 10. And step 3 tells you what your power of 10 is going to be. Right? So this is the first number between 1 and 10. Step 3, figure out what 10 needs to be raised to. In order to do that, you just need to count how many digits there are after the first non-zero digits. Right? So there's going to be this many here. Right? And that's what your power of 10 is going to be. There's 30 digits after the 1, so it's going to be 10 to the 30. Right? So that's the 10 to the proper power, and overall we have 1.989 times 10 to the 30 kilograms. Okay, and that's our scientific notation. Large negative numbers are exactly the same. When I say large number here, I could mean either positive or negative, but either way, I'm talking about large in magnitude. So I would consider 5 trillion to be a large number. I would also consider negative 5 trillion to be a large number, right? Because I'm just talking about basically how far that number is away from 0. Right? So if you're dealing with something like negative 5 trillion, it's going to be a very, very, very similar process. Right? Let's just to give a concrete example. Let's say that I think the U.S. debt to China is a little over $1 trillion right now. Right? I'm writing a negative here because it's money we owe. First step: find the first non-zero digit. It's going to be a 1 again. Then place a decimal right after it and write as many digits as you can until there's only zeros left. Step 3, count the number of digits after the first non-zero digit. It's going to be 3, 6, 9, 12. So 1.11 times 10 to the 12 with that negative out front. Okay, but pretty much exactly the same. Let's do a little bit of practice here. So go ahead and pause the video and then write these 3 in scientific notation on the form associated with the video. Okay, so these are the answers that you should have gotten. Notice that for this third one, we still have a bunch of zeros here. That's fine, right? Remember, you are only supposed to stop writing digits when only zeros remain. So you can't really stop like right here. You have to keep on going until you get past the 4. If your answers do not look like this, go back, see if you can figure out why. And if you can't, note it on the form or let me or Professor Polito know, and we will have a look at what went awry. Okay. Now let's talk about very small numbers. These run into exactly the same problem as large ones do. They take up a lot of space on the page. Here's the mass of an atom, right? Obviously very small, and of course, you have a lot of digits to write it out. It's even a little bit more annoying to write this out in full because there's no commas here, right? So it's very easy to lose your place when you're writing this out. So let's figure out how to put this very small number in scientific notation. Again, by small here, I mean very small in magnitude. So either positive and very close to 0 or negative and very close to 0. The first 2 steps are exactly the same. Find the first digit that is not a 0. It's going to be a 1 again. It's not always a 1. It's happened to be a 1 every time so far. Okay. Then place a decimal place after that. Write all the digits that are not up until there's only zeros left. So 1.67377. Step 3 is the only different one. Right? We are actually going to count how many zeros come before the first non-zero digit. Right? So that's going to be all of the zeros in pink. Notice that I am very much including the 0 that comes before the decimal. Right? So there are 27 zeros. You're going to take 10 to the negative 27. Right? So 1.67377 times 10 to the negative 27. Okay? Do some more practice here, right? Try to write these 2 in scientific notation. These should be your solutions for this. Again, note on the form if that's not what you got and you can't figure out where you went wrong. Okay, 2 more short topics and then we'll be done with this video. Sometimes you'll be dealt a number that is not quite in scientific notation, like this one, right? It's got a power of 10, but this first number, the coefficient, is not between -1 and 10, which it's supposed to be in scientific notation. So we need to somehow move this decimal place over. Right? So here's the steps to follow here. Excuse me. First, move the decimal place over until the coefficient has magnitude at least 1 and less than 10. Right? So basically, move this over 1, 2 places. Right? And remember how many places you moved it over. Next, you need to adjust your exponent accordingly. For every decimal place you move over to the left, right, you're going to increase your exponent by 1. Right? The idea here is that when I move my decimal over to the left, I decrease the magnitude of this number. Right? In order to keep the value of this overall number the same, when I move this over 2 to make the magnitude smaller by 2, I need to increase this power by 2, right? So this is going to go from 10 to the -8 to 10 to the -6, right? To basically counteract this step we just took. For every time you bump the decimal to the right in step 1, you decrease the exponent by 1. Basically, if you are going to inflate your coefficient, you have to deflate your exponent. So our final answer here is the coefficient, the -7.3234 times 10 to the -6. All right, try your hand at this. Here's the mass of an electron. Right? On the form, write this in scientific notation. Here are the steps that we had on the previous slide. All right, you should have gotten something that looks like this. Again, note if you did not and could not figure out what went wrong. Okay, last step, let's talk about how to go in reverse. Here's a number in scientific notation. How do we take it out of scientific notation? Okay. If 10 is raised to a positive power, like it is here, just move the decimal that many places to the right, adding zeros as needed. Right? So in this case, where the decimal was originally right here, right next to the 9, so you're going to go 1, 2, 3, 4, 5, 6. You're going to have to add a 0 and another 0 here. So 1, 2, 3, 4, 5, 6. If 10 is raised to a negative power, move the decimal that many places to the left, adding zeros as needed. Right? So for example, if this was my original number, right, I need to move this to the left 5 spaces. So 1, 2, 3, 4, 5. Okay? Try it on your own, right? This is the mass of a dust particle. Right? Write this out of scientific notation, just as a regular number. Should have gotten something that looks like this. We moved the decimal place over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's the end of this video. I will see y'all in the next one.